Okay, so next example, we have another rational expression that we're trying to find a limit of. And this time it's a one-sided limit. It's the limit as x approaches 4 from the right. Notice I have a quadratic in my numerator and a quadratic in my denominator. I'm going to zoom in just a little bit. So I'm going to factor both of those. The limit as x approaches 4 from the positive side of this quadratic over this quadratic. Now, being that this is a calculus class, I'm really not going to spend a lot of time talking about all of the techniques for factoring quadratics. You should not be here if you haven't mastered that. And if you need to refresh on it, definitely refresh on it, especially if it's been a while. But we do so much of this, we're not going to talk about all the basics of, factoring quadratics. I'm going to jump straight to what this factors to. You should be able to do this. X plus 5 times x minus 4. That's my numerator. Okay, down here in my denominator. I think I might have a typo for this one. Just want to double check here. Yeah, I'm missing a 6. I think that got deleted. This is supposed to be x squared minus 8x plus 16. So I'm just going to write that in. This one is actually a perfect squared trinomial. It factors to x minus 4 quantities squared. Okay? So when I'm trying to evaluate this limit, I'm going to do what I did before and do some canceling. Now this x minus 4 can cancel with one of the x minus 4s down here, but there's still another one since I was squaring that. So this is the limit as x approaches 4 of x plus 5, that's still in my numerator, over the one remaining factor of x minus 4 down in my denominator. And again, we're approaching from the right here. All right. Now at this step, there's no more canceling to do, and I'm running into an issue if I try to use direct substitution. Because if I plug 4 directly into this function, then I'm dividing by 0. So that's not defined. But it's interesting to note that this case is a little bit different than the previous example, because if I plug 4 into my numerator, I don't get another 0. I get a non-zero number over 0. And that's a special case of these types of limits that we're going to be addressing next. So let's first see how we can maybe attack what's left here. I can't plug anything in. I can't simplify this anymore. What approach should I be able to take now? Well, if all else fails, we can fall back on some of our techniques from section 1.1. In particular, I can try doing like a numerical approach and see if that gives me anything useful. So I'm trying to see if I did that here. Yeah. So I'm not going to plug a ton of things in. I'm just going to plug a couple of numbers in. Remember, we're approaching 4, but from the positive side or from the right. So when I'm plugging numbers in for x, and I'm going to call this f of x so I can just write it like that in my table. If I plug numbers in for x, I want to pick numbers that are close to 4, but slightly larger than 4. So I'm going to plug maybe just 2 values in to see if some kind of trend starts to arise. 4.001, 4.0001. Okay? So these numbers are very close to 4, but I'm being careful to choose numbers that are still larger than 4 because I'm approaching from the right. Now these would be plugged directly into your function. Use a calculator for this, and really we're going to be using this function. So I could even be calling this f of x right here instead of this one, just because it's simplified. But if you do that, use a calculator, plug it in, see what you get. In this case, I get 9,001. Too many zeros. 9,001. In this case, I get 90,001. In fact, if you wanted to, you could do one more because there is a pattern that arises here. It seems that every time I add another 0 in here, I'm going to pick up another 0 there. This would give me 900,001. And hopefully you can see that as x gets closer and closer to 4 from the right, the function that I'm evaluating the limit of is getting larger and larger without appearing to slow down, without appearing to approach anything. So this appears to be going to infinity. And that is, in fact, what's happening. So this limit goes to infinity. Now, remember, what we're actually saying when I write this down is that the limit doesn't exist. Even though I'm saying it equals something, This is just notation to say that the limit is failing to exist because it's never slowing down. It's continuing to grow indefinitely in the positive direction, okay? So this limit does not exist, it approaches infinity. We can generalize what happened in that example with kind of a general rule here. So if we're looking at a limit of this type, where it's the limit as x approaches c of a function over another function, and if the numerator is going to some non-zero number as x goes to c, but the denominator is going to 0 as x approaches c, then in any of those cases, we will always have a limit that approaches either infinity or negative infinity. And notice we break it down into a bunch of cases here, because oftentimes you will see a different thing happen if you approach that number from the right compared to when you approach it from the left. So for example, as we approach c from the right, that rational expression might be going towards infinity. But if we have the same rational expression here and the same number c here, the only difference is that we're approaching it from the left. It's possible that that might be approaching negative infinity instead. It could also be approaching positive infinity, but these two can be doing different things. So these, the point though is that we will always get one of these cases if the numerator goes to a non-zero number and the denominator goes to 0. Okay, so let's take a look at this example down here. The limit as x approaches 1 of this function. And I think there's another typo. This was supposed to be a plus right here. Not sure what happened. I've got a couple of typos in here. That's a plus. So I have x cubed plus 5x minus 2 in my numerator, and I have x squared, or x to the fourth, plus 2x squared plus 1 in my denominator. Okay, so what we're going to do is evaluate the limit of the numerator and the denominator as x approaches 1 separately. So the limit as x approaches 1 of my numerator, that's x cubed plus 5x minus 2. Now this is a polynomial. Direct substitution works, so I plug a 1 in. 1 plus 5 is 6, minus 2 would be 4. That's what I would get from plugging 1 directly into this. If I plug 1 directly into my denominator, what happens? The limit as x approaches 1. No. I'm sorry, I made a mistake. I did not have a typo there. That was supposed to be a minus. Now I'm seeing what I did wrong. X to the fourth minus 2x squared plus 1. Sorry, that is what we wanted. So in this case, as x approaches 1, we can use direct substitution again because this is just a polynomial. Plugging 1 in directly would give me 1 minus 2 plus 1. That's 0. Okay? I get a 0 out of that. So this is one of those non-zero numbers over 0. So that means that this thing will definitely not exist. It's going to do one of these types of behaviors here. And the question is, which one is it doing? Actually, I think the typo that I was seeing here was actually this was supposed to be a one-sided limit. I'm going to make it a plus there. So we're going to approach from the right. Okay, now I want to notice something. As x approaches 1, my numerator is always going to be really, really close to 4. So 4 is a positive number. My numerator is guaranteed to be positive. The question is, what's going to be happening with my denominator? Okay, so I want to plug 1 in, or numbers that are very close to 1, but just slightly smaller than 1, or slightly larger than 1, because I'm using a limit that's approaching from the right, to see if the number I get here is still positive but close to 0, or if it's negative and close to 0. So try plugging in, like, for example, 1.01. If I plug 1.01 into this, that's 1.01 to the fourth minus 2 times 1.01 squared plus 1. Okay? Do we get something that's positive or negative? meant to do this one in advance and I didn't, so I'm going to try plugging that into my calculator here. I'm going to see what I get off to the side. 1.01 to the fourth minus 2 times 1.01 squared plus 1. So I get a very small number as we're expecting, in the sense of it being close to 0, but it's positive. I get 0.000404. Okay? In fact, if I were to be plugging in numbers that are even closer to 1, but still slightly larger than 1, I still get a positive number here. So what that tells me is that as we approach 1 from the positive side, I'm getting a positive number over a positive number, but because my numerator is going to some non-zero number and my denominator is going to 0, it's going to grow indefinitely, and it's going to give me a limit that goes to positive infinity. So the limit as x approaches 1 from the positive side of x cubed plus 5x minus 2 over x to the fourth, that was not a typo before, minus 2x squared plus 1, the typo was this. This is going to fail to exist. It's going to go to infinity. Okay? So that's what we're looking at for that problem. A couple more examples, and then we should be good to go. 2 pages. Yeah, 3 more examples. So this first one here, I want to find the limit as x approaches negative 2 of 2 over x plus 1 over x plus 2. Or if the limit does not exist, then we want to show the way in which it fails to exist. Now, the tricky thing about this one is, again, if I were to evaluate this limit with my numerator and my denominator separately, so 2 over x plus 1, that's a rational function plus a polynomial. I can distribute the limit and evaluate each of those using direct substitution. If I did that, then I'm going to get negative 2 down in my denominator. 2 over negative 2 is negative 1 plus 1, that's 0. If I evaluate my denominator the same way, limit as x approaches negative 2 of x plus 2, then I'm going to have another 0 when I plug that negative 2 in using direct substitution. So this gives me 0 over 0, which is an indeterminate form. Okay? That tells me that the limit may or may not exist, but I have to do more work on this to figure out what exactly is going on. So how do we approach this then? I want the limit as x approaches negative 2 of 2 over x plus 1 over x plus 2. Okay, so when we have a more complicated looking expression like this, the goal is to try and simplify it first. Now, we can't factor anything in this case the way that we did in that previous example. However, this is something that some people will call a complex rational expression. What it means is we have rational expressions sitting inside a larger rational expression. And if you notice this 2 over x, I'm going to call that a mini rational expression because it looks small compared to the whole thing. What we want to do is eliminate the denominators from those little mini rational expressions. And the trick to doing it here is to multiply this by x over x. This is a valid thing to do because unless x is equal to 0, which won't matter because we're not approaching anything near 0, this is just a number that's equal to 1. And by multiplying this by 1, I'm not changing anything. But the benefit of that is if I put these guys in parentheses and then distribute the x's in, the first thing it's going to do here is cancel the x that's in the denominator right there. So this becomes the limit as x approaches negative 2 of the x's cancel, and I have 2. Don't forget the x is also distributing to that 1 there, so it becomes 2 plus x. Down here, I could multiply that x in. That would give me x squared plus 2x, but I'm actually going to choose to not multiply it in. I'm just going to leave the x sitting on the outside of those parentheses for a second. And my reasoning for doing that is by leaving the denominator in factored form, I can now see that I have a 2 plus x and an x plus 2 showing up in the numerator there and denominator there. Even though the order of addition is different, Addition is commutative, which means these two expressions are the same and they can cancel each other out. That leaves me with the limit as x approaches -2. Now remember, if everything in a rational expression, either the numerator or denominator, cancels out, it leaves a 1 behind. So there is a 1 right there, 1 over x. At this point, I have a different looking rational expression, but now we don't have any issues with direct substitution. My denominator is not 0 anymore if I plug -2 in directly. In fact, if I plug -2 in directly, I get -1/2. Direct substitution came to the rescue at this point. Okay? So that right there is my answer. And it took some simplification to get to that point. That's basically the big trick, or the big thing to take away from this section, is some algebraic manipulation can make these limits doable. Okay, a couple more examples. Next one, I want to find the limit as x approaches 16 of the square root of x minus 4 over x minus 16. And then if it doesn't exist, we'll talk about how it fails to exist. So up here, I took the limit of my numerator and my denominator separately to see if I got that 0 over 0 indeterminate form. I wrote it out in this example, but in general, I'm not going to use time to write that out because it's an easy mental check. You can just do this in your head. If I plug 16 directly into my numerator, which is how I would evaluate that limit, then I get the square root of 16, which is 4 minus 4, that's 0. Down in my denominator, 16 minus 16, also 0. So I can see immediately I have one of those indeterminate forms. So I'm going to go straight to a step where I can simplify. I get the square root of x minus 4 over x minus 16. This one looks different than the previous example. It's not a complex rational expression, but I am going to do a similar step. I'm going to multiply by another rational expression, which is also equivalent to 1, because again, that won't change the value of anything. And what I'm going to multiply by this time is the square root of x plus 4 times the square root of x plus 4. Okay? Now, why did I choose to do that? Well, this expression looks very similar to the numerator. The only difference is that where I had a minus here, I have a plus here. We call these two expressions conjugates. Root x plus 4 is the conjugate of root x minus 4. It's something that we do when we have an expression with two terms where at least one of those terms has a radical in it. What this does for us is it's going to multiply these two expressions out in a way that eliminates the radical, and it's really helpful. So I'm going to let you verify that when I multiply those out, I get x minus 16. Okay, again, hopefully you're comfortable enough with your algebra, you know about things like difference of squares and how those factor, to be able to do this multiplication immediately in your head without having to think through any steps, because this one is one that you should know. My denominator, kind of like the previous example, I'm going to choose not to multiply it out. It's actually more helpful to leave it in factored form. This is what it would look like. That's a plus. Okay? The reason I wanted to leave it factored is because now I have this x minus 16 in my numerator, which cancels with the x minus 16 in my denominator. And now I've got the limit as x approaches 16 of 1 over the square root of x plus 4. Now, even though my denominator still has a square root in it, that's not really the issue. The issue before was that I had an indeterminate form. If I tried to do direct substitution, I got a 0 in my denominator. That doesn't happen anymore. Watch, if I plug a 16 directly into my denominator, square root of 16 is 4, and now I have 4 plus 4, which is 8. The 1 in my numerator is not changing, so I get 1/8 as my limit, okay? Very important technique to remember, multiplying by conjugates when you see radicals there. That helps in the evaluation of these limits. I have one example left to talk about, and it's this one right here. So we want to find the limit as x approaches 10 of the absolute value of x minus 10 over x minus 10. Now the trick to this one is to think of the absolute value function as a piecewise function. So off to the side here, I'm going to say this. The absolute value of x, notice it's not exactly the same function. We're starting with the absolute value of x. But the absolute value of x can be thought of as a piecewise function by defining it this way. It's equal to x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. This gets people get a little tripped up with this because they see that minus sign there and they think that that means negative x. And even though that's normally how we would read that, this is actually a positive number even though there's a negative in front of it. And why is that? Well, remember, we only use this expression anytime the x that I'm plugging in here is already negative. So that's what it means if it's less than 0. If x is negative, then putting another negative sign in front of it makes it positive. And that's what happens with absolute value functions. If they're already non-negative, then the absolute value doesn't do anything to it and it leaves it alone. It keeps the x. But if x is negative, then it gives us the opposite of that. It gives us the absolute value, which is the positive version, which I can think of as just taking the opposite of that negative number. Okay? In our case, we're looking at the absolute value of x minus 10. So one way of thinking about that is this way. The absolute value of x minus 10. I can think of that x minus 10 as taking the place of the x up here anywhere that x appears. So a lot of these are going to change. I'm going to get, instead of x there, I get x minus 10 there. And this x becomes x minus 10. This negative x becomes negative x minus 10. Notice I'm putting the x minus 10 in parentheses so that this opposite sign right here doesn't only affect the x in the front, it affects the whole thing. And then this x becomes x minus 10 less than 0. Now, in this case, I'm going to leave these expressions written as they are, but I'm not going to leave these inequalities the way that they are, because in a piecewise function, it's really more beneficial to only have an x here. So on both of these inequalities, I'm going to add that 10 over. That means I can think of this way. X minus 10 if x is greater than or equal to 10. Negative quantity x minus 10 if x is less than 10. Okay? Now what I want to do is use this piecewise function in place of that expression, okay? Notice we're taking the limit as x approaches 10, but as we approach 10 either from the right or from the left, we're using different expressions to evaluate this. So kind of like we've seen with these piecewise functions, go like this. X minus 10. Kind of like what we've seen with these piecewise functions, we want to break it up into two one-sided limits. If we're taking the limit as x approaches this number where we split into a different function, and then see if those limits agree or disagree with each other. Now, this piecewise function is just what the absolute value of x minus 10 is equal to. And we're taking that absolute value of x minus 10 and dividing it by another expression. So we're using this piecewise function to only deal with the numerator here. Okay, let's think about this for a second. If we're approaching 10 from the left, then I want to use numbers that are less than 10. Coming over to my piecewise function, x is less than 10 shows up here, which means I'm using this expression. So the absolute value of x minus 10 will become this expression just for this limit. Negative x minus 10 over x minus 10. Now that I don't have that absolute value there, I can see an x minus 10 in my denominator and in my numerator. Those will cancel each other. And that leaves me with negative 1 over 1, which is negative 1. So the limit as we approach 10 from the left is negative 1. What is that limit if we approach 10 from the right? So again, I'm writing this out. But now, if I'm approaching 10 from the right, I'm using numbers for x that are slightly larger than 10 to approach 10. And in my piecewise function, if x is larger than 10, we use this. We use x minus 10 as opposed to negative quantity x minus 10. So that numerator just becomes x minus 10 now over x minus 10. And clearly I have a number over itself that's going to be equal to 1. That limit goes to 1. Notice the two limits disagree with each other. I have negative 1 here, I have positive 1 here. That tells me that the limit does not exist. So I could say that the limit as x approaches 10 of this does not exist because it did ask us to say how it fails to exist. It's not an infinite limit. It's that the two one-sided limits disagree. So I would write this. This is not equal to the limit as x approaches 10 from the right, x minus 10 over x minus 10. Okay? So this is my answer, does not exist, but here's my justification for it. Okay? That's going to wrap things up for section 1.2.